welcome to this problem walkthrough. Today, we'll dive into LeetCode problem number 2207, titled Maximize Number of Subsequences in a String. In this challenge, we'll explore how to strategically insert a character into a string to achieve the maximum number of desired subsequences. Let's get started with a detailed breakdown of the problem and its solution. In this problem, you're tasked with maximizing the number of times a given two-character string, called pattern, appears as a subsequence in another string text. A subsequence is formed by deleting some or no characters from the string without rearranging the order of the remaining characters. To achieve this, you are allowed to make exactly one character insertion anywhere in the string text. The goal is to figure out the maximum number of subsequences of pattern that can be formed after this single insertion. The input includes the string text, which has a length between 1 and 100,000, and pattern, which is always two lowercase English letters. The output is an integer representing the maximum number of subsequences of pattern possible after the insertion. For example, if text is abcd and pattern is AC, the initial number of subsequences of AC in text is 0. By inserting the character C at the end of text, the new string becomes abcd. Now, there are 4 valid subsequences of AC: that at index 0 pairs with the C at index 6, that at index 1 pairs with the C at index 6, and so on. This gives us a total of 4 subsequences of AC, which is the maximum possible in this case. Therefore, the output is 4. In another example, if text is ab and pattern is ab, the initial number of subsequences of ab in text is 4. To maximize the subsequences, you can insert the character A at the start of text, resulting in the new string ab. Now, there are 6 valid subsequences of ab: that at index 0 pairs with the B at indices 3 and 4, that at index 1 pairs with the B at indices 3 and 4, and so on. This results in a maximum of 6 subsequences of ab, so the output is 6. Finally, consider the case where text is at and pattern is AA. Initially, there are no subsequences of AA in text. By inserting another A at the end of the string, text becomes AA. This now forms one valid subsequence of AA, where the A at index 0 pairs with the A at index 1. Hence, the maximum number of subsequences is 1. The problem also includes constraints to ensure efficiency, like handling cases where text is as long as 100,000 characters, or where there are no matching characters in text. It's important to design a solution that works efficiently across all edge cases, such as repeated characters in text or very small inputs. To solve the problem of maximizing the number of subsequences for a given pattern in a string, we need to determine the best way to insert exactly one character. Let's start by considering a brute force approach. In this method, we examine every possible position in the string, including before the first character and after the last. At each position, we insert either the first or second character of the pattern and then count how many times the pattern appears as a subsequence in the modified string. This process is repeated for each position, and we track the maximum count achieved. While straightforward, this approach has a significant drawback: the computational cost. For a string of length n, we perform n insertions, and for each insertion, counting the subsequences can require another n operations. As a result, the overall complexity becomes n squared, which is not efficient for larger strings. To address the inefficiency of the brute force approach, we can use an optimized method that precomputes useful information about the string. The key insight here is that the number of subsequences of the pattern depends on how many times the first character of the pattern appears before a given position and how many times the second character appears after that position. To leverage this, we can precompute 2 arrays, one to track the count of the first character of the pattern from the start of the string to each index, and another to track the count of the second character from each index to the end. With these prefix and suffix counts prepared, we can efficiently evaluate the impact of inserting either of the pattern's characters at each position in the string. By combining the precomputed counts, we can calculate the potential increase in subsequences in constant time for each position. This reduces the overall complexity from n squared to n, while maintaining accuracy. The optimized approach is based on a few critical observations. The main realization is that the number of pattern subsequences is determined by the alignment and frequency of the two characters in the pattern. Instead of explicitly simulating each insertion, we use the pre-computed prefix and suffix counts to estimate the effect of each possible insertion in constant time. To implement this, we first compute the prefix counts for the first character of the pattern and the suffix counts for the second character. Then, we iterate through each position in the string and evaluate the number of new subsequences that would result from inserting either character at that position. Throughout this process, we keep track of the maximum subsequences formed. While the brute force method may be simpler to grasp initially, it falters when handling larger strings due to its inefficiency. The optimized approach, on the other hand, is both efficient and scalable, reducing the complexity to O(n) while ensuring correctness. This balance of performance and clarity makes it the preferred choice for solving this problem effectively. In this problem, we are tasked with maximizing the number of occurrences of a given two-character string, called pattern, as a subsequence of a longer string, text. To do this, we are allowed to insert exactly one additional character into text at any position. A subsequence is a sequence derived by removing some or no characters from a string without changing the order of the remaining characters. For instance, in the string ABC, both AC and ABC are valid subsequences. The challenge here is to strategically choose the position and the character to insert either the first or second character of pattern in order to maximize the number of subsequences in the form of pattern. This requires us to carefully analyze the structure of text and determine the optimal insertion point. To solve this problem, we start by identifying the key idea behind the algorithm. The goal is to compute the number of subsequences in text that match the pattern after the insertion. For this, we can use a running count of occurrences of the two characters in pattern. As we iterate through text, we keep track of the cumulative count of the first character of pattern, let's call it pattern 0, up to the current index. Additionally, we track the total number of pattern subsequences formed by pairing pattern 0 with the second character, pattern 1. The optimal insertion point depends on two factors: the number of pattern 0 characters before the insertion and the number of pattern 1 characters after it. To execute the algorithm, we initialize variables to track these counts, one for occurrences of pattern 0 so far, another for the total number of pattern subsequences formed, and a third to keep track of the maximum possible count. We also start by pre-computing the total number of pattern 0 and pattern 1 characters in text for efficiency. Once the pre-computations are complete, we perform a second pass through text to evaluate each possible insertion point. At every index, we simulate inserting either pattern 0 or pattern 1 and calculate the resulting number of subsequences. If we insert pattern 0 at a given index, it pairs with every pattern 1 that occurs after the insertion point. Conversely, if we insert pattern 1, it pairs with every pattern 0 that occurs before the insertion point. After evaluating each case, we update the max_count variable if the current insertion results in a higher number of subsequences. Additionally, as we iterate through text, we dynamically update the running count of pattern 0 to reflect the cumulative number of occurrences up to the current index. To ensure completeness, we also account for edge cases, such as inserting pattern 0 at the very start or pattern 1 at the very end of text. Once all positions are evaluated, the maximum count of subsequences is stored in max_count, and we return this as the result. A few key insights make this algorithm both efficient and effective. First, pre-computing the total occurrences of pattern 0 and pattern 1 allows us to avoid redundant calculations during the main iteration, ensuring that the algorithm runs in linear time. Second, dynamically maintaining the cumulative count of pattern 0 as we iterate through text enables us to efficiently calculate the number of new subsequences formed by inserting pattern 1 at any index. Finally, by evaluating every possible insertion point, the algorithm guarantees that we identify the optimal position for maximizing the count of subsequences. These strategies work together to ensure both the correctness and efficiency of the solution. This algorithm relies on simple yet effective data structures to achieve its goals. We use integer counters to track the cumulative count of pattern 0, the total number of pattern subsequences formed, and the maximum count of subsequences after an insertion. These counters are updated dynamically during a single pass through the string, which minimizes memory usage. The input string's text and pattern are treated as immutable, and no additional string manipulations are performed. In terms of complexity, the algorithm runs in linear time since it involves only two passes through text, one to precompute counts and another to evaluate insertion points. The space complexity is constant, as the algorithm uses only a fixed number of variables regardless of the size of text. This makes it both time and space efficient, suitable for large input sizes. This Python implementation solves LeetCode problem number 2207, maximize number of subsequences in a string. The problem asks us to find the maximum number of occurrences of a given two-character pattern as a subsequence in the string after inserting one character. The function maximum subsequence count begins by extracting the two characters of the pattern, A and B. We initialize two counters, count_A to track the number of occurrences of A in the text, and count_B to track the total number of valid subsequences formed by the pattern of. Next, we iterate through each character in the string text. For every occurrence of the second character B in the pattern, we add count_A to count_B. This step ensures that all previously seen AS can form subsequences with the current B. Additionally, if the character is A, we increment count_A to keep track of how many AS are present. After traversing the string, we calculate the result by considering the two possible insertions to maximize the subsequences. We can either insert A at the beginning of the string or B at the end. Inserting A maximizes the count of A and hence increases the number of valid subsequences, while inserting B maximizes the count of B. The result is the sum of count_B and the maximum of either count_A, representing all AS in text, or text.count, B, representing all BS in text. This ensures that the subsequences are maximized depending on the insertion. The algorithm runs in O(n) time complexity, where n is the length of the string, as we make a single pass through text. It uses O(1) additional space, making it efficient for large inputs. The solution is designed to handle edge cases such as empty strings and patterns where both characters are the same. This is the Java implementation for LeetCode problem number 2207, maximize number of subsequences in a string. The logic mirrors the Python solution, with explicit use of Java's type declarations and utility methods. The method iterates through the string to count occurrences of the first and second pattern characters, updating the subsequence count dynamically. It calculates the final result by considering inserting the first character at the start or the second character at the end of the string. The use of Java's chars, stream for counting and math.max ensures clarity and efficiency. To solve this problem, let's start with the first example where the text is abba and the pattern is ab. First, we extract the characters from the pattern, A is at and B is B. Next, we initialize two counters. Count_A starts at 0 and will track the occurrences of it in the text as we traverse it, while count_B also starts at 0 and will keep count of the valid subsequences formed so far. Now, we traverse the text character by character. In the first iteration, the character is A, so we increment count_A to 1. In the second iteration, the character is B, which means this B can form one subsequence with the previous A. Therefore, we add count_A to count_B, making count_B equal to 1. In the third iteration, the character is C, which does not affect either counter, so both count_A and count_B remain unchanged. Moving to the fourth iteration, the character is B again, so we add count_A to count_B, increasing count_B to 2. In the fifth iteration, yet another B appears, and we add count_A to count_B once more, resulting in count_B being 3. In the sixth and final iteration of traversing the text, the character is A, so we increment count_A to 2. With the traversal complete, we calculate the result by considering two options for inserting a character. Option 1 is to insert A at the start of the text. This adds the count of B in the text, which is 3, to count_B. The total becomes count_B plus 3, or 6. Option 2 is to insert B at the end of the text. This adds count_A, which is 2, to count_B. The total then becomes count_B plus 2, or 5. The maximum of these two totals is 6, so the result for this example is 6. Now, let's look at a second example where the text is AAA and the pattern is AA. Again, we extract the characters from the pattern. In this case, both A and B are A. We initialize the counters with count_a set to 0 and count_b set to 0, as before. As we traverse the text AAAA, in the first iteration, the character is a, so we increment count_a to 1. In the second iteration, the character is again a. This allows us to add count_a to count_b, making count_b equal to 1. We then increment count_a to 2. In the third iteration, the character is a once more. Again, we add count_a to count_b, updating count_b to 3, and then increment count_a to 3. In the fourth and final iteration, the character is a. As before, we add count_a to count_b, making count_b equal to 6, and increment count_a to 4. Now we calculate the result. Option 1 is to insert a at the start of the text. This adds the count of b, which is 4, to count_b. The total becomes count_b plus 4, or 10. Option 2 is to insert at the end. This adds count_a, which is also 4, to count_b. The total again becomes count_b plus 4, or 10. The maximum of these two totals is 10, so the result for this example is 10. For the third example, the text is XYZ and the pattern is AB. We start by extracting A as A and B as B from the pattern. The counters are initialized as usual, with count_a set to 0 and count_b set to 0. As we traverse the text, none of the characters match either A or B. In the first iteration, the character is X, so there is no change to the counters. In the second iteration, the character is Y, and again, the counters remain unchanged. In the third iteration, the character is Z, and still, there is no change. At the end of the traversal, both count_a and count_b are still 0. To calculate the result, we consider the two options. Option 1 is to insert it at the start of the text, which would add the count of b, or 0, to count_b. The total is count_b plus 0, or 0. Option 2 is to insert b at the end of the text, which would add count_a, or 0, to count_b. The total again is count_b plus 0, or 0. The maximum of these two totals is 0, so the result for this example is 0. To analyze the time complexity of our solution, we observe that the algorithm processes the input string text in a single pass, which makes it O, n, where n is the length of the string. Let's break this down step by step. First, initializing the characters from the pattern takes constant time, O1, since the pattern always contains exactly 2 characters. Then, as we traverse the string text in a loop, several operations are performed for each character. Checking if the current character is B is a simple comparison and takes constant time, O1. If the character is B, we update the variable count_b by adding the current count of A occurrences. This is another constant time operation, O1. Similarly, checking if the character is A is again O1, and incrementing count_a when the character is A also takes constant time. Since these operations are repeated for every character in text, the traversal contributes O(n) to the overall time complexity. Next, we analyze the final calculation step. Here, the algorithm computes max, count_a, text.count, b. The function text.count, b, scans the entire string to count the occurrences of b, which takes O(n) time. Comparing the result of text.count, b, with count_a to compute the maximum is a constant time operation, O1. However, since text.count, b, dominates this step, the final calculation contributes O(n) to the total time complexity. When we sum up the traversal and final calculation steps, we get O(n) plus O(n), which simplifies to O(n). Therefore, the overall time complexity of the solution is O(n). Now let's examine the space complexity. The solution operates with a constant amount of extra space. Specifically, it uses a few integer variables like count_a, count_b, and the characters a and b, all of which require O1 space. The input string text and the pattern are not modified, and no additional data structures, such as arrays or dictionaries, are created. This means the algorithm performs all its operations in place. Furthermore, since the solution is iterative and does not use any recursion, there is no additional memory allocated for a call stack. As a result, the overall space complexity of the solution is O1, as the memory usage does not scale with the size of the input. When comparing the optimized solution to a brute force approach, the efficiency of the current algorithm becomes even clearer. A naive solution would involve generating all possible subsequences of the string text and checking each one to see if it matches the pattern. For a string of length n, there are 2 to the power of n possible subsequences. Checking each subsequence for a match takes k time, where k is the length of the subsequence. This results in an overall time complexity of O2 to the power of n asterisk k, which is exponential and impractical for large inputs. In contrast, the optimized solution avoids the need to explicitly generate subsequences. Instead, it directly counts the occurrences of A and B while traversing the string and computes the number of valid subsequences in a single pass. By reducing the time complexity to O(n), the optimized solution offers a dramatic improvement over the brute force approach. Finally, let's consider the best, average, and worst-case time complexities of the algorithm. In all cases, the time complexity remains O(n), because the algorithm always traverses the entire string text and performs the same operations regardless of the input's content. The text.count (b) operation also requires scanning the entire string, which is consistently O(n). The number of A and B characters in the string does not influence the runtime, as the algorithm's structure ensures a linear execution time. Mathematically, this is justified by observing that each character in the string contributes a constant amount of work during the traversal, leading to O(n). Adding the traversal and the counting step gives O(n) plus O(n), which simplifies to O(n). The space complexity remains O1, because no extra memory is allocated beyond the fixed variables used by the algorithm. When solving this problem, there are a few common mistakes to watch out for. First, it's important to understand the difference between subsequences and substrings. A subsequence does not need to be contiguous, which means you can skip over characters in the string while maintaining order. Misunderstanding this can lead to logic errors when counting occurrences of the pattern. To avoid this, a two-pointer approach or dynamic programming is often reliable for handling subsequences correctly. Next, large input sizes can pose a challenge. If the string text has a length of up to 10 to the power of 5, algorithms with quadratic time complexity, like O(n squared), will likely time out. Instead, you should aim for an O(n) solution, which can be achieved using techniques like prefix sums or pre-computations. Lastly, it's easy to assume that the 2 characters in pattern are distinct, but that's not always the case. For example, if pattern equals AA, you'll need to specially handle repeated characters by counting combinations, such as using the formula NC2, which calculates the number of pairs that can be formed. These adjustments ensure your solution handles edge scenarios robustly. Another common pitfall is overlooking edge cases. Examples include when text is empty, when the pattern doesn't appear in text, or when you're inserting characters at the beginning or end of the string. These special situations can cause unexpected behavior, so it's essential to test them explicitly and verify that your code handles boundary conditions. Additionally, character insertion can easily become inefficient if you simulate every possible insertion by creating new strings for each position. This approach can rapidly become computationally expensive. Instead, you can use counters or prefix and suffix arrays to calculate the contributions of potential insertions without actually constructing new strings. These optimizations not only improve performance but also simplify your implementation. In interviews, understanding and clearly communicating the scope of the problem is crucial. For instance, if pattern contains repeated characters like AA, clarify with the interviewer whether special handling is required. This shows that you're thinking critically about the problem requirements. Additionally, once you recognize that O(n squared) solutions are infeasible, it's a good idea to discuss optimization strategies early on. Techniques like prefix sums, sliding windows, or greedy approaches can often lead to efficient solutions. Don't forget to highlight edge cases during your explanation, such as when text is empty or when the 2 characters in pattern are the same. This demonstrates thoroughness in your thought process. Finally, be ready to discuss trade-offs between space and time complexity. For example, you might use prefix arrays to save time at the cost of additional memory, and being able to articulate this trade-off can leave a strong impression. If you're interested in related problems, there are several on LeetCode that can help solidify your understanding of subsequences. Problem number 115, distinct subsequences, involves counting subsequences using dynamic programming and is a great way to practice handling similar challenges. Problem number 392, is subsequence, focuses on the basics of subsequences, making it an excellent starting point for beginners. For more advanced practice, problem number 583, delete operation for two strings, involves dynamic programming in the context of string operations, while problem number 1092, shortest common supersequence, dives into subsequence construction. Exploring these problems can deepen your familiarity with patterns and techniques that are directly applicable to maximizing subsequences. To wrap up, there are some key insights and patterns that can greatly enhance your solution. One powerful strategy is leveraging prefix and suffix contributions. By counting how many pattern 0 characters appear before an insertion point and how many pattern 1 characters appear after, you can efficiently calculate the effect of inserting a character at any position. When the two characters in pattern are distinct, the two-pointer technique is another efficient way to count subsequences. For a more strategic approach, you can evaluate each position in text and calculate the maximum gain in subsequences achieved by inserting the chosen character there. Finally, if pattern 0 equals pattern 1, the problem simplifies significantly, as you only need to count pairs. This can be optimized using combinatorial math, such as calculating combinations of pairs with the formula NC2. These techniques not only improve efficiency but also simplify the logic of your solution, allowing you to handle various cases with confidence. Thank you for following along. To recap, we solved a fascinating problem using prefix sums and efficient string manipulation to maximize subsequences. Remember, these techniques are valuable tools for tackling similar challenges in interviews and real-world scenarios. We hope you found this walkthrough helpful. Stay tuned for more problem-solving content, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!